Okay, so you were supposed to have taken notes on the first couple pages from the PowerPoint. Now, here's the thing about most of the information on those 2 pages, we're not really going to worry about it, stress about it. If you choose, or if you are in Physics 2, then you will go into a lot more detail. So if that, some of it, excuse me, kind of felt like physics-ish, you are right. So physics focuses a lot more on energy and the work that can be done, and they apply it with the gas laws. So really where I want to kind of pick up, and there's a few things, endothermic, exothermic, those slides, but we've already talked about some of those, but I would say star that, exothermic, endothermic, that's what this unit is all about. So the very last slide, we kind of talked about Q, meaning heat. So Q is heat. You can add this somewhere, not necessarily on this slide. Temperature, remember, temperature is not heat. Temperature is what we use as a measurement of heat, but if it says what is the change in heat, you don't just subtract the temperature to say the temperature changes equals the temperature, the change in heat. Delta H, that is enthalpy, heat of the solution, enthalpy. But notice we're going to call it the heat of solution. So in chemistry, because notice not physics, so don't go over to Mr. Brown and say that what Mrs. Mahoney said. In chemistry, because we assume pressure stays the same, delta H and Q, we get to use them interchangeably. So that really will come into effect when we are doing some calorimetry calculations today. We're going to really use this effect. So what happens a lot in these problems, you will calculate Q at some point in the problem, and then they're going to turn around and tell you to calculate delta H. I can use Q to calculate delta H. And in fact, a lot of times they are the same things. What they'll do is maybe change units. A lot of times this is calculated in joules. This is calculated in kilojoules per mole. So they kind of normalize it. So the way we calculate then our enthalpy changes. Stoichiometry. We looked at one of those problems. That was the last thing on the notes. Calorimetry, Hess's law, heats of formation, bond energy. So really today we'll just review on stoichiometry and calorimetry. Friday we'll look at the other ones. So this was one, remember, excuse me, on the problems, if you look at 5 different ways, it's kind of like buffers, but not in buffers in a bad way, just meaning you have to recognize what am I given to be able to recognize how do I calculate it. So this you probably already copied down, but what I want you to look at is how do I know it's stoichiometry? Well, they gave me a balanced equation. One balanced equation. That's kind of a key too. And they gave me a heat that was part of that equation. Typically, they're going to give it to you in grams or some way to find moles. All of those are your clues that that's going to be a stoichiometry problem. So then if it's stoichiometry, we need moles. You can set it up to solve, and that's going to be how much energy did you lose for that mole. Now, one thing with the signs, delta H is for negative, or delta H is for negative. Delta H negative means exothermic. You can get away with the sign change by sometimes using the words absorbed or released. So remember, delta H negative means that system has released energy. Also remember this, when you have data, the temperature of the surroundings will increase. So when you see the temperature going up in a system, not in the system, excuse me, you're collecting data and the temperature goes up. We never measure the direct system, by the way. We always measure the surroundings. That's how you're going to know it's an exothermic reaction. Okay, calorimetry. We did maybe barely touched on this in pre-AP. So calorimetry is some clues. It's always going to be happening in a calorimeter or a coffee cup. They're going to say a coffee cup calorimeter. It's like a clue. How do I know what I'm doing? They do the coffee cup because it's a good insulator. So you will have this styrofoam. Here's my system. So inside, this is where the reaction is taking place. You're going to have an initial temperature, you'll have a final temperature, and you're going to calculate how much heat was gained or lost in that reaction. Now, the calorimetry, we are going to find delta H, but you're actually going to find Q first. Now, a couple things, they can have a piece of metal heating up or cooling down, or you can have a reaction, or you can have even just dissolving. But we're going to use Q equals MC delta T. This formula is on your formula chart. This is called MCAT. It's our nickname for it. So Q equals MCAT. Sometimes it's a big Q, sometimes it's a little q. That doesn't matter. So M would be mass. Okay, now I would use mass if my C is in grams. C is specific heat capacity. Sometimes Q might be moles per C. Delta T, I would use mole if they give me my C in moles. This unit, the thermo, is so important of the units. You have to pay attention to the units. You have to label your answers. Saw a lot of sloppy labels on the acids and bases. You forget your molarity, you forget your things. You can't get away with that here. A lot of times you will not get the point if you do not have it correctly labeled. So specific heat capacity is an intensive property that how much heat do I need to add to make this substance change temperature. And typically they standardize it is for either 1 gram of the material or for 1 mole. If you were in my class in pre-AP, I kind of gave you the example on a hot August day in Texas, 2 o'clock in the afternoon. You walk out. We're assuming everything's the same mass. So you see a pretty pool. You have surrounding it a concrete walkway, and then you have some really nice black wrought iron chairs. So they've all been out in the sun. That's our only heating source. So they're all out in the same heating source. We're assuming that they all have the same mass. So are they all going to be the same temperature? If so, we can pick somebody to go sit on the chairs. I bet you're all kind of doing nose goes. Nobody's going to sit on the chairs because they're going to be hotter. The cement will be hot, not as hot as the metal, and the water is going to be the coolest. That is specific heat. They all take a different amount of heat to raise the temperature. Typically, this is given to you. So look at, here's some common ones. So look at water. It's 10 times the specific heat of metals. That's why water does not heat up as fast, and it also doesn't cool down. So that's why in the morning those wrought iron chairs are pretty cool, but the water hasn't really lost that much heat. So it's the amount of energy to heat or cool. Sometimes we forget about the cooling. Heat of fusion and heat of vaporization are for phase changes, and we're going to kind of wait on that, and we're going to talk about that on Friday. So Q equals MC delta T. Typically, again, how do I know I'm going to use this? Well, what is delta T? This is the change in temperature, so it's final minus initial. So another way you know, oh hey, I'm going to use MC delta T is when you have 2 temperatures. You see the temperature change, you can calculate Q. So common ways these problems. Let's look at a couple different ones. Calorimetry, where you're taking a huge assumption. So here's the big assumption in a calorimetry problem. That heat lost is going to be equal to heat gained. So heat lost is going to be equal to the heat gained. So if I take this block of molybdenum and I heat it up, and then I'm going to put it in the water. So the temperature of the water initially was initially 24.6 degrees. Look what the water did. The water heated up. Why did the water heat up? because the metal cooled down. So it's a transfer of heat. We assume that you get 100% transfer and nothing is lost to the cup or to the environment. This is why when we do this activity, we are going to actually do it on a computer, because we don't get very good results, because that assumption in a teenage high school lab doesn't always work so well. What do I need to do? Where do I put it? And we don't get very good results. So we're going to use a computer simulated. So look at what we do know. I have to go, okay, well, I have grams of water, so here's my mass of water. So you kind of have to ask what heated up, what cooled down. Here's my initial temperature, but this is of the water. Here's the mass, okay, but this is of the metal. So I have two different things. I'm going to have a lot of data. This temperature is the initial temperature of the metal. Then this final temperature, this is of the metal and the water. They come to the same final temperature. That's what you have to wait for in the data. So it's, what do I have enough information? So I have the mass of water. I know the specific heat of water. That's a constant. I just gave it to you on that other sheet, 4.184 joules per gram degree C. And I know the temperature change of the water. So I can calculate the heat gained, and I know the heat gained because look what the temperature did, it went up, of the water. So plug in, and that is the heat gained by the water. Well, the heat gained by the water is going to be equal to the heat lost, because where did that heat come from? It came from the hot piece of metal. So heat gained equals heat lost. So what I'm doing right here, heat gained equals heat lost. So this is Q. All I'm doing is doing Q equals MC delta T again. All of this was for my water data. This time I'm going to use all my metals. Now, technically this should be negative. And this should be a negative temperature because you do final minus initial. So this would be 28 minus 100. That's where the 72, but it should be negative. So your two negatives will cancel out. You can never have a negative specific heat and a negative mass. So make sure with the negatives, remember heat gained, that's positive, heat lost is negative. So we just plugged everything in, then you just do your algebra, and we get the specific heat. So I had to erase my marks there. Then you get your specific heat of 0.27. It's like, does that make sense? Yes, metals are going to have specific heats that are less than 1. Okay, that's one way with just a metal. Okay, the more common way that we see it is more of a reaction or dissolving. So look what we're doing this time. 400 grams of ammonium nitrate was added to 100 milliliters of water. And again, polystyrene, what is that? That's a coffee cup. The water is initially at a temperature of 22.5. Look at all this data. So what you have to just do is what data goes with what. This time it decreased. So if it decreased, is this endothermic or exothermic? The temperature went down. So temperature goes down. We know that this is endothermic. Sometimes that's a really good thing to say because if you don't have the correct sign, you're not going to get the point. So it went down because the system, that chemical system, needed energy. It stole the energy from the surroundings, so the surroundings got colder. And we always take data from the surroundings. So to determine the heat of solution, look at the difference. Heat of solution is delta H of ammonium nitrate in, look at our units, kilojoules per mole. Assume that the heat absorbed or lost by the calorimeter is negligible. They're always going to tell you that. That just means you can assume heat lost equals heat gained. So you have to say, okay, what do I know? Well, I have a temperature change for the water, and I know, so again, they would give you specific heat of water is 4.184. Okay, now this is where you have to be careful. What is in my cup? I have 100 milliliters of water. Okay, they're also going to say assume the density of water is 1. And so 1 gram equals 1 milliliter. So that's how I can assume that my 100 milliliters is actually 100 grams. So that's where my 100 grams came from. But what else is in there? Oh, there's 4 grams of my solid. Don't forget, what is my cup? What is my cup? If you can picture it, then you're going to get that point, because if you forget to add those masses, you're not going to get the point. So we're going to use Q equals MC delta T. I have to erase my drawings again. So it's always Q equals MC delta T. Got to figure out where I've got my things. Okay, so look at what we did. So that should be space. So I just plugged in, but right here, this is where that 104 grams came from. This is the water plus the 4 grams. Specific heat of water. This is how much the temperature changed. This time final, 19.3 minus 22.5 give me negative. So you saw the heat, that it was actually a negative heat. That's just the water lost heat. Where did the heat go? The heat went to the dissolving. So it went to the system. So in joules, I paid attention to my units. Remember, there is 1,000 joules in 1 kilojoule. That needs to just be in your head, needs to be second nature. So that's where I have 139 kilojoules. So now we're going to use, heat lost is equal to heat gained. This time my heat is delta H. It is delta H. We get to make that assumption. So my delta H is just a negative 139 kilojoules. But it's not just kilojoules is what they asked for. They wanted it per mole of what's causing the heat. So kind of go back, what's causing the heat? The ammonium nitrate is causing the heat. So that means I need to figure out how many moles of ammonium nitrate were in there that caused that temperature change. So we're going to use molar mass of ammonium nitrate. So I had 0.005 moles of ammonium nitrate, and reminding ourselves that heat lost is negative. Heat gained, well, we know it's endothermic, so we know our answer has to be a positive delta H because it's been gained. The system gained it. So just take your heat that's now positive, divide it by the moles, and that's how we get 28 kilojoules per mole. Okay, this math we did right here, this is what you're going to be doing in the activity. So you're going to go on, and I've found the site, it tells you how to get to this site, and you have a whole list of compounds. And when you have your compounds, I want you to pick one that's endothermic and one that is exothermic. You might have to play around a little bit. You're going to have to select the mass of the solid. I would keep it around 5 grams or so. Take the mass of water, whatever mass you want. Again, I would have at least 100 milliliters. And then you're going to have to record. So I want you to record the data like you're actually doing it. You're going to have to collect your final temperature, collect your initial temperature, tell me the mass of both things. Then you will use that data to calculate Q. You know Q is equal to delta H, but I want it in kilojoules per mole. When you calculate Q, since specific heat is in joules, because use 4.184 joules per mole, because we're assuming the water is the same. So you will calculate that in joules. You have to change it to kilojoules. So like I said, this calculation is what you have to do in the activity. And you can work with a partner, talk it out, and you can figure out how to show all of your work and answer those questions on the little bit of the worksheet. So Friday I will answer any questions, and we're going to talk about our last few ways of how to calculate delta H, and we'll pretty much be done with chapter 6 by Friday. Have a good day, and I will see you soon.